So now that you're at or near the end of an introductory ordinary differential equations course, if you were to take another course after this, it could be partial differential equations, but it could also be dynamical systems. And so that deals with ordinary differential equations mostly, and it's the qualitative analysis of nonlinear systems of ODEs. So pretty much you give up on trying to solve them exactly, get an exact solution, and instead you make qualitative statements about them. And so there's a few things. So there's nonlinear ODEs. They can have multiple nonlinear systems ODEs. They can have multiple fixed points. So this, for instance, is modeling a pendulum, where one direction is position in radians and the other direction is angular momentum, yeah. And so there's centers and there's spirals, and then the lines I think go this way. I forgot all my arrows, but you end up with this phase portrait that's much more complicated because it's a nonlinear system. You can also get things that called limit cycles that are more global. So when you have a center, it's just in a circle after circle after circle. When it's nonlinear, the centers aren't circular necessarily, they can deform, so this one becomes more football shaped. But this one is just a periodic solution that doesn't have any periodic solutions right next to it. So there's a point in the middle, it's unstable, all the stuff from the middle spirals outward and goes towards this periodic solution called a limit cycle, and then everything outside the limit cycle is also attracted to the limit cycle. And it kind of can go a roundabout way sometimes, but it all gets there. So those are limit cycles, those are studied. You also study iterative functions, so like the logistic map is one. You make these cool things called cobweb diagrams, so you kind of go forward and forward. You have a function, it's kind of like forward Euler's method, where you take, x sub 1 is some function of x sub 0, then x sub 2 is some function of x sub 1. You keep going through, and then there's also bifurcations. That actually usually gets covered first. And pretty much you have a nonlinear system. There can be no fixed points, and then all of a sudden this fixed point can appear. That's kind of weird. And then that fixed point can actually split apart into two more fixed points. And then you also have strange attractors, which is probably the coolest of all. So this example is the Rossler attractor. A more famous one is the Lorentz attractor. And I usually keep it over there, and I have my little makeshift shelf here. There's a video if you want a really zoomed in view of it. And I'm not going to touch it because I'm afraid it'll fall. All right. And then if you do want to study it, and you're not, if you're in school and you take a course on it, if you are taking a course on it, you're probably using this book. So it's Nonlinear Dynamics and Chaos. This is the second edition. And the really nice thing about it is if you aren't in school, the author, Stephen Strogatz, actually has recorded lectures, a full course that he taught. I think it was Cornell in 2014. And this book pairs with it. You could also, this is the second edition, the third edition also, it has one more chapter on the Kuramoto model. So the lectures recorded in 2014 won't cover that, but it covers chapters 1 through 12 otherwise. And there's also a solution manual. And disclaimer, I did write the solution manual, so that's a little plug for me, just so I'm up front here. But yeah, if you were to self-study with this, you would have answers to all the odd exercises. So that's that, and hopefully, if you want to study this, you can take a course on it, or you can self-study and you can watch the online lectures. You can go through the book and also problems in the book, and you can see, make sure you're doing at least the odd ones correctly.